All right.
Thanks.
Thanks for that. Yeah, the timelines that Graham indicated just had me reflecting about some current things going on in British Columbia. And one, when I first got in the business, it was I was a summer student for Utah International in 1969, and that was the year we landed on the moon. Well, the other good to go message that year, didn't probably register in many of you people, was that Utah said go ahead with the development of the Island Copper Deposit. It was found in 67, the decision to go was made in 69, and it was producing in 1972. 5 years. And right now there's 3 deposits in BC, Gaylord Creek, Cucho, and Morrison. 2 are porphyries and 1's a massive sulfide. These are found 25, 30 years ago. The industry is still struggling to get them out. One's got some Aboriginal problems, and the Aborigines aren't the problem per se, but it hasn't been sorted out. One was just massive cost overruns. It's a joint venture at Gaylord with Teck, and the development cost went from an estimated, I think it was 438, 42 change, and they added an extra $1.5 billion for the slope stability and tailings were required, in part for environmental purposes. And then another one is the Morrison Deposit found by Noranda years ago. A few mines were produced in that part of British Columbia, but this one never got to production, and it has environmental issues around it. So even in places we call safe havens, with defined assets of defined value, they're stuck. And I think that's one of the things that Richard Chody has particularly highlighted, that and Graham now for us, that just because you found them doesn't mean they're going to get off the mark. There may be some real impediments. It doesn't have to be in one of the stands. It doesn't have to be in a country with an unstable politics. Well, BC sometimes you'd say they're unstable. They're odd, I guess. Is, they're West Coasters. What can you do with it? So my part of the story is I've got the outline here of I call the Geophysical Toolkit. And this is not, this is really aimed, or I tried to aim with this, is to say what have we currently got available to us in a fairly synoptic way. You'll hear more specific examples through the day in the individual case studies as to how some of these technologies are used. But I'm just trying to give an overview, since we have a broad range of people's experience in this in the room here and exposure as to what's available to us. And so I'll start with, this is a comment that I think was made a few years ago by a colleague of mine and probably known to some of you. And I think it's still a very apropos for where we're going with exploration undercover. We can actually see quite deep. We can image geology quite deep. It's very difficult, though, often at those depths to have, say, the clarity that the oil industry enjoys with seismic. And it's all about the physics of it. When you send an acoustic wave, which is the primary technique in oil, down even kilometers depth, they can maintain extremely high resolution. There's not the attenuation, whereas everything we put into the ground or get back, potential fields, electromagnetic energy, the further off it is from the detector system, which usually is the surface, maybe it's in a low-flying aircraft. Sometimes it's in a borehole. We'll probably have to do more of that. And that's what I was thinking about your kilometer deep story there on that zinc. The borehole gravimeter that's been just come out with Syntrex might be the sort of thing that could help de-risk that project, to look around and see if there was excess mass. I mean, kilometer is scary for everybody, I'm sure. So it's there. We can see things, but it's blurry. And I don't think Graham's investors are any different than any other people who put money in exploration. They like confidence, more confidence than we can probably often deliver. Now, one thing I'll just say here is I won't say just a personal observation, but I think ultimately it's the people that have to de-risk it. The technologies will only take us so far. The decision made by Mark and his group, I think there clearly had to be some people there that said, okay, given all the vagaries of it, we need 10, we've only got 3 targets, a gut feel, and that probably still is very important, even exploring under depth. This is kind of the global suite of things. I apologize, it doesn't go into a huge amount of detail, but it covers, say, the potential fields, electromagnetic, passive and active, seismic, surface and VSP, and not to say that the seismic world is restricted to oil and gas. I'll have a nice little vignette later on that the HiSense people provided showing some very interesting results from the Nevis-Corvo area. The electrical techniques, we're going to have a talk by Jonathan Rudd from Quantech on this, and mixes of this from the folks from Oz and Lisa Vella, who worked on Carapatina, radiometrics. I expect there will be some, even though it seems to be a very, call it explicitly superficial technique. It depends on what sort of environment you're in, where those rocks are. If you understand that they may be actually, you may through structural relationships have brought older rocks on top of younger ones. Radiometrics could actually carry some signature of things from depth. And then I do put, because geophysics does have that kind of mystery about it, there are some other things. I know there's work one company is putting into muons. It doesn't have an explicit, probably, greenfields exploration opportunity. It's more something in a brownfields environment for mass detection, and there is some innovative work on radar. I understand a group in Scotland is doing some things that seem to be kind of in the scientific fringe zone. We're not, when I say that, it's not to discredit them, but they're not clearly, they haven't come through the cloth or through the mist yet to understand what they can contribute. And of course, there's often a lot of people that will claim they have something that is very miraculous in geophysics, and you know, usually often for naught too. But so we'll look at the range of things. One of the first things I like to point out, and this is a gravity story, but it applies to a lot of geophysics. Rob Ellis, a good friend and colleague, put this together, you know, sort of like a Carl Sagan. There's an infinite number of solutions to every geophysical inversion. Well, we start off with these two little bodies here, and what he's done is calculate the gravity tensor, and then he's done an inversion to it. And each one of these models here, including one which looks pretty darn close to the actual source bodies, you've got a couple little, looks like a little spit on the rock here, and then some a Christmas tree and a fuzzy blob. A paleo surface, that's actually pretty legitimate type of model. Some very distorted bodies here in the correct one. All of these are part of a mathematically correct same error fit to those models. And this is what inversion, unconstrained inversion, really gives us. You can constrain things, but it usually requires some additional knowledge. And often in the greenfields environment, this is a challenge to know where we're going to find this. John McGaughey yesterday in his presentation said that with the rapid prototyping of geology and geophysical forward models, we could potentially help not just constrain, but provide things which explorers can look at and then make the judge as to whether the world is actually sort of looking like that in a real sense. And so we know we have a lot of potential solutions, but geological intuition can help eliminate a large number of those and then allow us to focus on the ones that are most likely. It's still not necessarily a target, but it does certainly allow you to move forward with some sort of model building in areas that otherwise would be fairly mysterious. Unconstrained inversions, most of you have probably seen something like this. The difference with this one, it's the scale, and that was a thing that Yagwa Lee cited yesterday in his talk. That, and John McGaughey, we can now start doing these inversions. We've got the computing power to basically allow us to pull apart terrain scale type models. Okay, this is a big chunk of the Abitibi where this was run. But I call these, and not to be negative to the people that did them, but they're fairly soulless things. They're things that really fit math. They don't fit geology implicitly, because we really don't know much what's going on at the sort of 30-kilometer depths that these have been built. It's the area of geological intuition, potentially the world that the MT people, or there's a few seismic transects in this environment, not much. There's a bit more MT. We really don't know about this. So if you put this in front of a Dick Silito type character, it's probably not going to be the sort of food that's going to allow him to say, I think there's an ore deposit there. It's more of a bit of a geomystery. And the industry is trying very hard to figure out how to add in a judicious way, in an effective way, to help constrain these models. At this sort of scale, it may be challenging, but certainly in the brownfields environment, where I think we have to recognize that's where the real assets of the mining industry typically are. This is the place that's our sandbox. This is where we're getting to learn how to do these things. And what I see is probably an ability to take these out into more greenfields environments and say, okay, fine, at an existing mine you may have 500 drill holes to allow you to do the constraint. Can we get at least part of the solution, part of the value of a constrained model with, say, 3 drill holes? This is kind of the question that confronts us now. How much real constraint do we need to make these models better and believable, and allow somebody like Graham and his intrepid band to go out and stake a patch over this and say, right, we're going to spend $10 million worth of our shareholder money to try and make a play on this. This is a result, actually, I harvested this from a paper given here at the conference. This is from Tasmania. They're starting to do constrained potential field, gravity, and magnetic models. I won't try and give you the story behind this, but there's certainly, I wanted to say, you know, we're not just lost in the desert here. We're actually making progress. But we need real data, and we need geological input and oversight on these things. Because otherwise, you know what geophysicists do. We sit there and just iterate to the smallest error fit. And the error fit is important, but it often doesn't carry the geological credibility that these things really need if they're going to be useful in exploration. One of the things that I found is maybe an underappreciated part of our toolkit, and it was from the era when we couldn't do inversion. There was a time then we actually, well, we sort of technically did inversion 30 years ago, but we did it with things we called type curves. And basically people would sit down and generate forward models, and they'd have these curves of characteristic response, either layering or discrete bodies, and you literally would sit down and try and match your data to a curve. And so you didn't have to do computing. You were in a form doing a form of inversion, but there was no real-time computing taking place. But there was a forward model, and this is a form of a forward modeling case where we were trying to interrogate a gravity gradiometer data set in the Athabasca Basin. And the concept was being presented geologically that we had alteration plumes sitting over top of the unconformity mineralization. And if any of you have gone looking for these or looked at the model, the mineralization itself at typical depths in the basin is impossible to see. It's very small. It is geophysically very anomalous, but it's far too small to be directly detected. What people typically go after is the big graphitic keel that extends down into the Archean basement. And that's part of the plumbing, part of the geochemical system that's allowed that deposit to be created. But there is direct evidence. Over top of these, there's a much larger cupola of alteration, either silicification, desilicification, along with a number of various clay products. And these are the sorts of things that start to become realistic to maybe be seen with something like a gravity survey. And there were a number of surveys flown in the basin in the mid last decade. BHP had some excess capacity and pushed it out into the basin, and we got a hold of a couple of these data sets and said, okay, this is the sort of data set we're looking at. What happens when we put these theoretical models into it? It's not inversion. This is actually, this is an inversion here of the actual observed Falcon data. But the forward models are dropped in. These little things here are what we generate as the suspected targets. And the idea being if we could see those, either the density highs or lows, then there was a chance in that data set we could recognize these and take these to, interested explorers and say, right, we actually have an ability to recognize that sort of alteration, which we don't believe had been done before. So it was kind of a hybrid thing. We had one inversion model in the form of the density data cube here, but then we put forward models into it. And that's a very powerful thing to have available because the forward model does not lie. It may be simplistic, but it's exactly what you constrain it as, a certain shape, certain density, and certain susceptibility. We know geology is going to be more heterogeneous, but as Dan Wood told us about large world-class porphyry systems, there's a lot of stuff there with the bulk property that we should be able to measure. In the case of porphyries, he called it the sulfur anomaly. It sounds very sort of fire and brimstone type thing. Terrain scale models. We're going to hear a bit more about this later this morning when Yagwa Lee talks about the SEAM project. But when I saw this is actually a numerical model of the Noranda camp. The horn ore body sits down in here, but you can see the sort of scale. This has all been created inside GOCAT. This was done as part of a large exploration initiative that Noranda, Falconbridge, and then Xstrata continued in the Abitibi to try and come up with that next generation, call it, of deposits in a mature environment. This is something which I think we I certainly believe groups like GA and CSRO are looking at building. The thing for me that I found curious is that while this was built by Noranda and actually was published, when I saw it in a paper by one of the students, Doug Oldenburg, students at the Inversion facility, UBC, actually Noranda, or I'll call them, they're now Glencore, had not made extensive use of this for their own modeling purposes. But if you hung susceptibility in here, if you hung density, conductivity, acoustic velocity, all of that could be generated as a forward model from this GOCAD solution, which is a pretty awesome database. So I think going forward, when you come into a greenfields terrain, this is the sort of thing that you're going to want to start constructing early on to help you frame targets within that environment. I mean, it's very difficult to see these individual things, but certainly there has to be some linkage between the overall geological package and the reason why there's mineralization in this particular area. I think anyways. We'll maybe hear more about that today. Ambiguity. This is a living, breathing one. The earlier one that I showed from Ellis was more of a kind of a hypothetical case. This was an actual exploration situation that a client of ours had to confront in the Athabasca. He had a, call it top-notch, high-depth investigation megatem survey. The unconformity sits down in here. While it is a sandstone by and large, there are shale units that are conductive sitting in there, and they can be quite unpleasant in terms of electromagnetic techniques in particular. So we've got an unconformity down here. It's about 700 meters, 800 meters. So the client had this result, and he said, well, I'm not confident that the airborne penetrated the bedrock. And what he was looking for were one of these graphitic shear zones. And he says, I don't really see that. I see some sort of waffly, shallow conductive horizon here, maybe a shale unit and maybe some saline material. It hasn't really addressed my exploration question. So he ran some magnetotellurics, and there's two inversions of this. This one was provided by the group that acquired the data, and in that particular case, they did identify a similar conductivity structure to the airborne, but they also came up with what you call it as a suggestive keel zone, which could be the representation of one of these graphitic zones in the basement. The client, however, decided that this was not really as robust of an anomaly as he might like, or a feature as he'd like, and he took it to an independent group who was expert in the processing of MT data. And that consultant basically came back with something that looked a lot more like just the airborne with no keel. So I showed this a few years ago in Saskatoon in one of their open houses, and of course the guys in the middle, they felt that they were being, grievously picked on. And I explained, no, it's not. We're just at the edge of uncertainty. Welcome to the real world. When you start going down 800 meters, this is the fuzzy part that Joel Jansen referred to. We may see things, they may appear, and they may disappear. We don't really know. We're at the limits of technology. Now, it would go back maybe to Graham, your story about the guys at Sirius, and would this be the thing that they would test? They might, and there may be something there. We actually don't know. I can't tell you. I think that particular company, as Graham alluded to, they found the cost of drilling so prohibitive in this environment, they all went to places like Namibia and Wyoming looking for shallow uranium resources, because the Athabasca just kills you when it comes to this drill testing. So uncertainty, we have to learn to live with that. This is another example. Again, God bless them. These are academics. They put this stuff out. What am I to say? But look at it and you pick up your jaw afterwards. But this is the same. It's a line of MT data there was a much more extensive survey. This is actually over the McArthur River deposit in Saskatchewan. So again, a deep conductor play. I don't think the depth here is quite the issue, but we have 3 independent sources of inversion code, and just take it on face value. It's the same data going into 3 different programs, and these are the outcomes. Okay, look for similarity, look for differences. Oh, that's the same guy. Where did it go here? This was state of the art 5-6 years ago. These are codes we're still using. And I think the people that wrote the codes are probably as good as anybody at running them. So again, this is the world of uncertainty in some of these techniques. If you get a brilliant result, you know, most people will only have one. And if you luck out and maybe say had the Mackey one, you'd feel really pleased. But if you handballed it over to somebody else, which many groups, and I understand in the oil industry do this, when they have high risk, high reward, high cost plays, multiple groups are asked to review the same data. Multiple groups. I think the military does the same thing. We can't just trust one team because they have their own set of expectations and limitations, even if they're all using the same software. In this case, they were using different software. So I won't say it's a good thing, it's not a bad thing, it's a thing. It's just something that when you go into the world, these are the things that happen. Of course, we always give you enough hope to keep you in the game, right? We never totally beat the bejeebers out of you. So here was one that we had a chance to work on. I got a couple of slides here. I'll zoom in. This is with the Geotech's new AFMAG, the ZTEM system. We actually were given we processed the data, and the client then, afterwards, gave us a DXF of a shale unit, conductive unit. And here we can see how a pretty good matchup down at 1.8 kilometers. So the inversion worked, the geological model was robust. And I can tell you, this looks good, and you say, oh man, everywhere we go with this technique, Witherly says we're seeing down 2 clicks. The problem is, if you take this out to around Neobabel, where it's very conductive, the ZTEM system will only see about as deep as a VTEM. It's only going to see down 200 to 300 meters. So you're scuppered as soon as you put a conductive layer in here. So, choose your technique in the right terrain, and you can get results which are pretty impressive. But you have to be heads up. Don't just believe the first guy that tells you about what you want to be doing. Here's another one in the legacy of deep exploration. This is the Nevis Corvo body and the gravity anomaly. I know it took some time to actually, I think, get people to believe there could be something that deep. And that's one of the, I went to dinner with Dan Wood, and he said probably more important than anything else he saw in geology was getting people to stop believing that things can't be true. Look over your shoulder. There's more things in heaven and earth that we ignore that are ore bodies than we care to admit. A lot of times the existence of anomaly or existence of an important outcrop has been known by many people over a long period of time. But it takes somebody, sometimes a person who doesn't know as much about it as others, not as experienced, to come in and say, what's that? And I think Nevis Corvo, I heard, had a bit of a story around that. We'll break in here a little, nice little couple of slides that the Greg Turner and Don Pridmore at Hisense provided. They had done some real work here, and I think it's always good to see some real data, so I slapped this in. Mature terrain, so again, as I said earlier, I think we're getting pretty effective in the Brownfields environments, doing things at reducing risk and targeting, combination of constrained inversions, borehole geophysics, all the sorts of things that help put some money in the bottom line. We've got here a little scenario slide. I'll just cut to the chase here. Where they shot the thing, they're basically some specs on the survey. I might, if I have to break out. Here's the takeaway slide, I think, though. This is what I saw, was this. Here's a scale bar of 200 meters. And even in most seismic sections, where I always wonder, how is it they draw these lines on these images, Where does this come from? What are they smoking? Colorado, it's okay to smoke now, too. It's awesome. it's as busy as a 7-Eleven. I sit there, waiting for my wife buying a lotto ticket, and all these people going into the Mary Jane store. It's amazing. So anyways, here's the massive sulfides here. So step down, 2, 4, 6, 8. Greg, is that honest to say? Something over 800 meters? 900? Yeah, awesome. It's great. You still have issues of grade and size, but detection is 90% of our game typically in the beginning. You need the drill to tell you the rest of it. So that's their little takeaway message. And yeah, to put this cube over top, and I assume that if you had additional data like MT or complementary deep investigative information, you could be pretty effective. This is one which has made the rounds, I think, around the world many times now. The tooth sitting on top of the jawbone. This being Olympic Dam with an overlay here of both some connectivity information, some rough outlines. There's kind of a dead zone, I think, in the seismic I saw on another slide. Is basically the idea being the intrusive is absorbing the seismic energy, and so it's not actually all the little layers. It's actually a zone where there's not much happening, but geologically it makes for a pretty good story. And again, like my unconstrained inversion from the Abitibi, we are getting down to basically the top of the moho. We can provide imaging information, but I mean, you've got to remember the scale across here. That's 40, and that's linear. That's 150, 200 kilometers. So it's not actually really a target scale, but it's a concept scale, which would allow discussions and ideas to take place around this in terms of what could be down there as a mineral play. And of course, you end up having to take a little piece of ground right at the top as being the. And 3D models. Not to disrespect all the wonderful stuff that the go-catters and leapfroggers and the rest of it. I saw this at an open house a couple of years ago. This is a series of acetates, and these are the samples that the guy had, and he sort of stuck them together in this little 3D model. You know what's valuable about this one? He believes it, he understands it, and he can show it to people, and he can speak to it. If you're sitting there in front of a giant, as somebody had the guy had the 3D goggles and everything, and it was the kid, of course, the video gamer. He was playing with this at the convention the last couple of days, and you say, okay, that's good. How do you actually embed yourself? And I remember a colleague, Alan King, once saying they've got a big visualization center in Sudbury, run by the Ontario government and the feds and everything, Monarco, I think it is. And I said, Alan, what do you think about because we in BHP, we were dabbling with 3D cave environments and things like this. And Alan said, as Alan can, he says, oh, Ken, it's good, once. And then you go back to sections and looking at your Geosoft maps and stuff like that. So, he's maybe a generational thing, but yeah, we used to generate this sort of thing fairly routinely, and just the way that this guy, he's a prospector geologist, very passionate about it. Some neat things on the modeling side. This is a bit on the back to like the forward solution style of things. This was a paper, or from a paper, just put out in Econ Geology in the last month or so, and focusing around the Bingham Canyon. And my colleague Donald Hinks is listed a co-author, and Donald, to his credit, he's a very unassuming guy. He says, these guys came over, they're from a university in Europe somewhere, I think, and he says, we talked about it all. He says, I gave them some ideas, but they did all the work, so really it's to their credit. But the idea is that can you actually look at some things in the upper crust with magnetic data that are now starting to provide some possibilities as to the formation. Here you've got a stock system here coming from below, and this laccolith feature, and the Bingham sits up on top here. So starting to look at mineral systems, taking that, say, that Olympic Dam model and going to the next step, starting to put some what-if questions in there that are constrained by real data. And of course, the Kennecott Rio Tinto people have an excellent magnetic data set over this area. And getting geologists to take the geophysical data, I mean, because the number of times that geophysics appears in econ geology is like, it's like a vampire at the blood clinic, right? It's very often they sort of end up. It's a bad place, You don't want to show too much geophysics. The guys get wobbly about it. But I think these graduate students and Rio Tinto, to their credit, provided them the data sets and gave them the motivation to try and think about it. So we've actually, for the next geophysical ASEG meeting, which will be in Denver next year, we're thinking about maybe trying to get a theme around this. Can we pull more of this geological modeling using geophysical data, because this would be a great place to put some gravity information as well, and a very good story. How many of you actually saw this article? Curiosity? Two people. Okay, 3. Good. It's a good read. I think it's a good read. Anyways, what we can do with magnetic data. This is just a snapshot of some stuff that we've done internally in Condor recently. The GSC. This is a piece of the Athabasca Basin. Here's Key Lake. MacArthur's up in here. The Rough Rider Zone and things are just off the edge here along this trend. This is the Fifth Avenue of Abitibi, the Athabasca Basin. The geological feature is much bigger, but this is really the address where all the major deposits have been found. And there are others. It's not the only place, but it's the prime real estate. We've got Key Lake right in the edge here. So here's the unconformity surface sitting here. This map here is totally derived from aeromagnetic data. And there's the unconformity line here. The interesting thing is that this is all the part that says, we all know what's going on here because this is outcrop. This is outcrop. And this is, sort of zero thickness, and then it's getting hundreds of meters and 500 meters over in here. And it's hard to tell on this image, I know. We'll say make it available. But the geology as mapped from the aeromagnetics, and we're not talking here unit A is so many gammas or such and such a texture, but just when you put a coherent image together using the geophysical data, it does not look like what even we call the mapped geology. Okay? The client focused on the area over in here where it's covered because all he has is drill holes to put it together, and so he was most excited about this. But you step off into what we consider in areas of known geology, and they aren't as known as we think they are. If you looked at the point data, which we always try and get a hold of, but is very seldom available, you would probably find that it's not in disagreement with what's over in here, but the rest of that is largely conjecture, And you'd say maybe at the time, back in the mid-70s or early 80s, it was the best of the day. But there's certainly, to Graham's point, being undercover doesn't mean under 500 meters. It can be under a relatively shallow amount of gravel and lakes and things are not blinding us, but covering things that really, the geology we think we know isn't always the case. So I stuck that in. I've high-graded a couple of slides here from Dan Wood has given a number of great presentations on this material, on the work that he and his team at Newcrest did at Acadia. This is what I consider a pretty cool slide showing in a progression, moving from the very shallow deposits and then uncovering the deeper ones, the Ridgeway one down here, and then the Acadia far east, which is actually under a significant amount of covered rock. I'll be interested if James has had a chance or knows about work of geochemical expression over this. I would expect we'd see geochemistry here, but if it sees it through here, I'd say that's a very exciting event, but I'll leave that for him to talk about a bit later. But this is the brownfields. This is the mature camp. You've got head frames, you've got resources, you've got company focus. It's a known mineral system, so not a problem, right, to put money into it. This is the IP anomaly over the top of Ridgeway. Okay, and everybody, Scott Holliday when he presented it at Exploration 07, and Dan say, this does not detect the deposit. But this is what he said a couple of days ago. He says it didn't find it, but it was found because of the IP survey. Because of the IP survey. And that's because, when you go back to this expression is seen as an alteration over top of the system. They knew what they were thinking about. They thought about in the third dimension. They didn't say, oh man, and I've got clients that say, oh, those numbers are too small. That can't be a porphyry. Can't be a porphyry. They're not thinking about that direction, right? They should be. But then you take this story and you carve it out and you stick it out and whoop, And this is in Canada we call this affectionately the moose pasture guy, you know, where you don't have the precedent, you don't have the head frame, and you going to get excited about that anomaly? Well, Jonathan will probably tell us you should, or you should go to a bigger Orion survey or something, but you know, it's a cost-benefit issue. We have really great technologies which if we put them in brownfields, we know the cost-benefit value is likely going to be rewarded to us, but it's often difficult to apply the same level of technology in high-risk areas because everybody's trying to keep their budgets down. So this is, sorry, not a seismic one, a little bit fast. LaLore, this is actually depth below surface. This eventually took Hudbay quite a while, but they came up with this very significant base gold-rich discovery, which is getting bigger and bigger. They've got hits down in here now, well below a kilometer, in a camp which historically, the 777 and the Flin Flon deposits are actually about 60, 80 kilometers to the west. In this particular area, in the Snow Lake area, they're all tended to be pretty small. But they've tagged on to something here which looks both size-wise, grade-wise, and the addition of the gold very, very significant. And this is some modeling that Daikun Yang and Doug Oldenburg at UBC have recently completed. Here they're doing some experimental work with 3D inversion on both heli-TEM and ground squid data. And you can see here, the airborne system sees it, but it's back to Joel, it's fuzzy, and it's certainly a lot sharper when you can go and do the groundwork. But again, you know, you don't go run ground squid out in a place where you have no control, typically, because you really don't have, why would you put the most expensive technology available in a place where you're not really sure what's going on? It's a kind of a conundrum how we apply our high-end, high-value resources to places that don't have, we need some way of upgrading these environments. Here's one that just came out recently, a review of some airborne EM, junior based in Sydney. They've got what we call their Halls Peak, New South Wales. A well-known consultant processed and reviewed this data and is suggesting, you know, this is being put out to the ASEG. They're actually seeing down 1,500 meters. So you get back to that one I had from the ZTEM survey. So we can image things down. Sometimes they're sharper than others, but there's some hope, but it's still difficult. I came up, as I felt I had to, with some sort of ranking, different scales, targeting and mapping, the different techniques. This will be in the presentation. I guess going forward, I don't personally see that there's any, in the 5 to 10 year period, that table is going to change markedly. I think it's the one we're going to have to live with. I think the way to bias it more to the medium, change the lows to mediums and the mediums to highs, and make the highs cubed, is the geological input that we can provide, the geochemical inputs we can provide, the other information, and the getting the explorers to sit down and think about these in ways that are beyond, say, the bump finding. Targeting, different scales, that was just some thoughts about how we put time and money into various scales. Richard had Minex had some stuff in his last presentation as well. So with that, my presentation is done. I won't ask for no questions. Anybody? Chris, sponsor.
Just a comment about inversions and unconstrained inversions. And calling them unconstrained. Actually, I don't like to call them unconstrained inversion. It's really semantics. We all know what it means, but there's really no such thing as an unconstrained inversion, because even all those gravity images you had up there, each one of those, as the algorithm chugs away, has exactly the same number of constraints. So unconstrained should much rather be called default, because all it means is that your constraints were chosen by someone programming in a corner office 15 years ago at UBC or Colorado School of Mines that you don't know, and they have no knowledge about your problem. So it's not actually unconstrained, it's just lazy.
Yeah, good point. The lazy the L inversion, the L norm, the lazy norm. It's actually a mathematical term. When you say that, it twigged a discussion I had with a client. He wasn't the recipient of the work we did, but he knows about the work. And in this particular case, we did an unconstrained, not lazy, it was arduous, but inversion. But we used the UBC code. And within that, there's certain things. That's one of the standards in the business. And the other one that gets a lot of use is written by a developer, John Payne, in Adelaide. And the client used that program. And it was interesting from my perspective that the UBC default, and this gets into the sort of thinking that the person who put the program together, they like to have things vertical. And so all the big sources tended to go to depth. Whereas the way that John Payne's code was run by the client, everything looked like laccoliths. It was all cut off at the bottom. And as an explorer geologist, I think those are very, very different. But they're both unconstrained. But what it means is that, like Chris is alluding to, there's actually engrams. There's DNA of the programmer in the code, whether you like it or not. And you may have to work very hard to put your own controls onto it. Otherwise, the defaults are going to be the things that the person who wrote the code thinks is sensible, which is usually an advantage. At least it gives you a starting point that doesn't make it look like gobbledygook. Anyways, I won't belabor that. That's anybody else? Okay. Richard Lane.
I like to see that you raise the issue of interpreted geological products as blurring the distinction between actual observation points and the interpretation and the inference. That subject really does make it more difficult to enter that geological information and its associated uncertainty into the geophysical modelling process. Because today's forum might well be renamed not exploration undercover, but exploration away from observation. It may be laterally, it doesn't necessarily have to be at depth. And most geological interpretations downplay opportunity or the potential for something to be there of interest for exploration. They tend to infer more of the same boring old. And people take that as, well, okay, well, that's all been visited and no longer prospective, when that's not actually true. Nobody's been there to see. So it's not necessarily undercover, but just away from the known. Maybe at 1 metre depth.
Yeah, well, Graham made that point. Undercover doesn't mean deep. It just means beyond our current reach of appreciation.